there, welcome back. We've been talking about exponential functions both in general and with the natural ones, with Euler's constant, 2.7181828, etc. Now we're going to get to the calculus part. We're going to talk about derivatives of those exponential functions, both kinds. There we go. And we're off to the races. And we're going to take a very, very brief look at the normal probability distribution function. If you've taken statistics already, you have run into that. It's the normal curve. And if you had, again, used that or run into it, you probably used it, but not in the calculus look to it. We're not going to get into it too deeply, so relax. So here we go. Let's get some derivatives on the way. And before we get too far into this, let's make sure I have my pen active. And let me sign in. Okay, I'm here. I'm hoping you're here. We're going to start out with that e part, e to the x, the one that's so nice and is used so often. It's not quite the same as when you have just any old positive number. E is very special. Now, we're just going to go through some of these. You don't have to worry about the limits. We're not going to really delve into that. But this is where e comes from. If you take the limit of 1 plus delta x, in other words, very close to 1, but then you take it to a power of 1 over delta x. Now, if you give this just a tiny bit of thought, 1 is a constant. Delta x is getting closer and closer to 0. So if this is getting very small, then this 1 over delta x is getting very big. So you've got something just a hair over 1 taken to a power that's getting very, very, very big. But the two sort of balance out each other, let's say, and we end up with a constant. Instead of it getting a lot smaller because of this, or a lot bigger because of this, it actually settles into 2.718 and so on. So this e is almost that if you let delta x be very small. Or if you're using h, as I like to use, then h is here and h is here. And this is approximately that. So we throw that approximation in. We start with the definition of a derivative, and we use e to the x instead of any other function. We use that for our f of x. Do the substitution. This is just a way of factoring that, because this, remember, is e to the x times e to the delta x. So we can factor out the e to the x, and we get this. This part here becomes just that. And anyway, you can see the rest for yourself. Eventually you end up with just e to the x. So what you've got is e to the x, and the derivative of that e to the x is e to the x. That means at any point on this curve, it's got that slope. The value of y and the slope are the same value at the same time. Almost eerie the way it matches up. Let's start off with a couple that I mentioned in class as a preview a week ago. Two derivatives functions. This is the basic one that we just looked at. It says if you just got e to the x, in other words, we've got this exponent, but it's just an x. Usually you'd see something a little bit more, quote, interesting, unquote. If it's just x, there's your derivative. Same thing. However, if it's a little bit more interesting, if what you've got for an exponent is actually a function itself, then our chain rule, again, gives us this. Instead of e to the x, we have e to the u. Works the same way with e to the u. The only difference is that if this is a function right here, then we have to take the derivative of what's essentially the inside function and get du dx. Now what can be handy, like in some of the other ones, when you're starting to take the derivative of some natural exponential function, is to find out what this is, and also at the same time take the derivative of the function u. And then you have it ready to do your actual overall derivative. So here we've got some functions to experiment with, and let's start with the first one. F of x equals 4e. Well, if you go back in your memory to taking derivatives, if you've got a function, let's call it g of x. If g of x is 5, in other words, a constant function, just like y equals 5, means the same thing, that y prime is 0. The derivative of a constant is a constant because if y is not changing, then the slope is 0. And this is an indication of how fast it's changing. So g of x in this case is 0. Since this is a constant and this is a constant, together they're a constant. So what do you get? It's not changing, so the slope is 0. Constant rule. Don't forget the rules. Next one. Okay, it's not just x this time. So here's our f of x. We want the derivative. And the derivative, we just write the same thing. Just copy that. 2x minus 1. Oops. 2x minus 1. Try to fix that a little bit. And then the derivative of the inside function, which in this case is 2. Clean that up a little bit. We have 2e to 2x minus 1. Do a few of these and you can get pretty quick at finding derivatives with the natural function. There's our chain rule. And that is it, simplified. Next one. More interesting, huh? Well, if we want the derivative of that, we're going to have to use the product rule. So x and e to the x, we're going to take the derivative of that, product rule, and put a plus in there. Then you'll have the derivative of x times e to the x untouched. And the rest should be mechanical by now. E to the x The derivative of that is just e to the x. So this is x e to the x. Looks vaguely familiar, right? And the derivative of x is 1. So it's just e to the x. There's your answer. And if you want to, you might write it like this. Since both those have e to the x, you could write it like this. E to the x times x plus 1. Bingo. You got your answer. Product rule. Simplify. Of course, they didn't factor it, but we did. We're a little bit ahead of them. Original function. We want the derivative. So, what do? First thing you might want to do is rewrite it. We don't want to use the product or quotient rule if we don't have to. So let's make this 1/2 e to the x minus 1/2 e to the minus x. We're ready to go. I guess I should have done this. Taking the derivative of that. That's just a rewrite. Okay, let's get down to business. On the first one, this is a constant, so leave that out front. And the derivative of this is e to the x. Over here, we've got a constant out front. Got e to the minus x, but this is not just x, so we have to take the derivative of the minus x. And there's your minus 1. A little bit of a cleanup or simplification. 1/2 e to the x, and this minus and the minus cancels out, plus 1/2 e to the minus x. And if you want to, you can write that. Since you get a common 1/2, you might wish to write this. And you might even want to do this just to compare them. E to the x plus e to the minus x all over 2, and then compare these two. Hauntingly similar, but different. Next. Oops. Sorry. Next one. We've got a quotient. However, you might prefer the rewrite first. We'll make this x to the minus 1. We'll put that out front perhaps. I guess it really doesn't matter. The derivative. Use the product rule. X to the minus 1. And the derivative of the second one is just e to the x. Plus, and we reverse the roles, the derivative of the first one is a minus 1. And the derivative of the second one, of course, is e to the x. What do we have? The derivative equals e to the x over x minus e to the x. If you want to, we could make this e to the x and 1 over x minus 1. It all depends on what you're going to do with the derivative, which way you'd like to write it. There's the quotient rule. They use that instead. It's up to you. Simplify. And I think this is the sixth and last one. Alright, looks like we don't need to do any rewriting. So the derivative of that one. We've got a product for this one. So I've got x. The derivative of e to the x is e to the x. It looks like we haven't done anything. Plus, and then we reverse the roles. The derivative of x is 1, and e to the x as the original. Next, minus. It's like a minus 1 out front, a constant. The derivative of e to the x is e to the x. And if I'm thinking chain rule, I'm thinking, okay, let's see, did I forget anything? Well, the derivative of this is just 1, so that doesn't change this one. So let's see what we've got. The derivative, you've got x, e to the x, and then you've got 1e to the x minus e to the x. So you end up with just x, e to the x. How curious. Bet you didn't expect that one. All right, next. Applications. This one's a little bit tricky, so you might want to take this a little slowly and write some things down as you go. What we've got is a telephone wire hung between two poles. So the catenary has this function that describes its shape. And if we want to find the lowest point in the wire, we can use our calculus, find the derivative of that function. Remember, just take it one step at a time. Don't get overwhelmed by what it looks to be. So we've got our constant out front, so we can forget about the 30 temporarily. The derivative of this, just write the same thing, and then the derivative of the inside function is right here. And then the second one, just copy that down, and then take the derivative of what's inside here. That's the derivative of the inside part. So you've got both of those have 1 over 60. So bring that 1 over 60 out front to make things a little simpler. This will give you 1/2. So what you've got is this, and that's your answer. If you want to, you could put each of those over 2, or you could put what's in parentheses in the numerator and a 2 in the denominator. It depends on how you're going to use this derivative. So we want to get back to our problem. Find the critical numbers. We set the derivative equal to 0. There you go. Multiply each side by 2. Looks a little bit better. Get it ready to solve. Add that e to the minus x over 60 to both sides. Looks simpler. And where do we go from here? Well, we've got two expressions here. Both of them have the same base. So if these numbers, this number and this number, are going to be the same, and you've got the same base, then the exponents must also be the same. It's one of the properties, very handy one. So x over 60 equals minus x over 60. Next, multiply each side by 60. Remember, very simple. Add x each side, and we know what the answer is. Here's our critical number. And because you know it's the lowest point, That's going to be a relative minimum of the function. There's our picture. And you can see it with this graph overlaid. You can see that it's a minimum on the interval -30 to 30. Notice the poles are 60 meters or feet apart, I forget. Let's say feet for the time being anyway. So it's halfway between the two poles. See? Halfway between the two poles. To see how much it sags, compare the height at each pole with the height at the minimum. So first of all, what's the height on one side? 67.7 feet at the left. On the right side, actually they're doing the middle first, middle next. Put the 0 in there, that's the middle point. If we look back here, in case you want some reference. Remember, this was the first one. Where am I? We did this calculation first. We put the -30 in where the x was. And right now we're putting the 0 in, which gives us the middle point. And then in a moment, we'll put the +30 in and see what the height is there. So back we are. There's the height of the wire at the left pole, the height in the middle, and the height at the right pole. You can see it's sagged. If you look at the middle one, it's 7.7 feet less than the height at either of the other poles. There's your sag. And just a quick one about normal probability distribution functions. You may remember, if you've taken statistics, that there's a normal curve, and you've probably either forgotten or wanted to forget what the equation looks like. That's the equation for the normal curve. It doesn't look quite so normal looking like this, does it? However, notice that this is the x, and all the rest of these are constants. This represents the mean for that particular curve. This represents the standard deviation. Standard deviation, of course, pi is a constant. All these things are constant. This is the normal probability distribution function for some statistics that have a mean of mu and a standard deviation of sigma. A little bit off-putting. You probably wouldn't be thrilled to do some calculus with this. However, remember, you've got constants all the way through this. This is the only variable. So it's not really that bad. I'm not expecting you to do this either. Just take a look at it. Sigma is the lower case sigma, by the way, in case you're a Greek, for example. Mu is the lowercase Greek letter mu. Standard deviation for sigma, or sigma is the standard deviation, mu is the mean. So for what's called the standard normal curve, the standard normal curve, we won't get into that too much, but the standard normal curve is a special one that has a mean of 0. That means you've got positive numbers, negative numbers, but the average is 0. And also a standard deviation of 1, which a quick translation means if you looked at all those numbers in this distribution of numbers, the average is 0, because you've got positives and negatives sort of canceling each other out. And the standard deviation means if you plucked one of those numbers out of a hat, the chances are that number would be about 1 unit away from the mean. 1 unit above or 1 unit below. On average, if you pulled out one, you could guess that it would probably be 1 away from the mean. And that's what it means. So we can find the first derivative. That's actually not too bad because of all those constants. Because remember, you got 0 for the mean, 1 for the standard deviation. Once you put those in, it cleans up a little bit. Notice you've got the constant out front, 1 over the square root of 2 pi. It looks weird, but it's just a constant. Think of it like a 17. And the rest of it, you can do. You really can do that. You'll have the product rule for these two pieces. You can copy this. That's easy, right? You can take the derivative of that. That's easy. You can copy that. You can take the derivative of that now. It's not that bad. It looks like that. That looks sort of bad. But actually, that's not too bad. And there's your second derivative. If you set that equal to 0, you can find that x is plus or minus 1, x at plus, the graph of that distribution, the standard, has an inflection point at positive and negative 1. And that's what it looks like. And 1 and negative 1 are where it turns around. Remember, inflection point means if I'm coming from the left to the right, which is the way we look at it, the curve is getting steeper and steeper until this point. That's the inflection point. After that inflection point, the curve starts leveling out. The slope gets less instead of greater. Your slope is still getting small, less and less, until you get to this point at x equals 1. Then the slope starts leveling off. And that's pretty much the story of the normal distribution.